This video is about applications of Moivre's theorem, and specifically it's about the roots of complex numbers in polar form and how to find them. So the first thing that we need to know before we can begin to actually apply de Moivre's theorem in this context is how do we write roots as powers? So for example, if we had the root of x, how would we write that as a power? Well, a square root is the exact same as an exponent of 1/2. And what about a cube root? Well, that's the exact same as the power of 1/3. When you have a fraction power, basically what's happening is that the top of the fraction is operating as a regular power and the bottom of the fraction is operating as the root. So for example, if I had x to the power of 3/2, I would have x to the power of 3 because of the numerator of the exponent, and a square root on that because of the denominator 2 in the exponent. So let's have a look now at an example of how to find the root of a complex number. So this is a pretty straightforward example. I've got a complex number, it's already in polar form, and I want to just get its cubed root. So bear in mind what the question is really asking me is to find z to the power of 1/3. So I already know about de Moivre's theorem. Again, don't forget this on page 20 of your log tables if you need it. So I know that if I apply a power of 1/3, then I'm going to apply that power to the modulus and then multiply the angles by it. I will have one extra little thing to take into account though when I'm dealing with a fraction power. And that is that before I apply the fraction power, I have to write my angle in general form. Okay, so you'll remember that from trigonometry. It's the exact same idea as in trig. It's just adding n360 or plus 2n pi if it's in radians. So this is my complex number z. I'm not going near the power of 1/3 just yet, written in general form. So I've got this n360 here and this n360 here. And the reason that I have to include this is, and you'll be familiar with this from just algebra, that when you want to get the root of something, you'll generally end up with more than one answer. And it's this n360 here which will allow me to access my multiple solutions. Okay, so now I'll get started on actually applying the power. So z to the power of 1/3, well, I've got my modulus here, which is 2√2. So I'm going to have to say 2√2 to the power of 1/3. And then I'm going to multiply the power by the angle. So 1/3 times 135 plus n360 plus I sine 1/3 times 135 plus n360. At this point, I can go off to my calculator and do a bit of evaluation. And 2√2 to the power of 1/3 is going to come out as √2. And then I'm going to multiply 1/3 by 135 plus n360, which gives me 45 plus n120. And that'll be the exact same angle in the sine part of the term also. So now I have my general form of the solution for z to the power of 1/3, but I want actual exact values. So now I'm going to have to substitute some values in for n. So just like with solutions from general form in trig, I'll start by subbing in n is equal to 0. And also just like with solutions from general form in trig, I will put in as many values of n as the number in the power. So you can see here that there's a 3 because we're looking at the cubed root. So I'll have 3 values of n. So I'll have n equals 0, n equals 1, and n equals 2. And it's just a question of subbing those in and then just tidying up your result. So I'm nearly there now. I'll just write my 3 final solutions then in their final tidied form, and I'm done in this case. And finally, here I have my 3 solutions. In some questions, they will ask you to write your final answers in the form a plus bi. So just watch out for that, and don't forget that's quite easy to do just using your calculator. So here's a second example then with a bit more to it. We're asked to solve z squared, where z squared is equal to -1 minus √3i, and z is a complex number. Now, a couple of things to watch out for here. First of all, there's a really common misconception here that what you're being asked to do is to square the complex number on the right-hand side. That's not what you're being asked to do at all. You're being asked to figure out what z is. So if we're trying to figure out z, we're going to have to figure out the square root of both sides. And of course, as we saw in our last example, a square root is the same as a power of 1/2. So we could rewrite this as minus 1 minus root 3i to the power of a half. Now, the second that we see a power on a complex number that is anything more complicated than just basic squaring, we're pretty definite we're going to be heading in the direction of de Moivre's theorem. So that's going to be to the fore of my mind, and I'm going to write that formula down just so that I know exactly what it is. Bear in mind that in the formula, the z they're talking about is the complex number that you're applying the power to. So in this context, this is the complex number. So this is the one that I'm going to have to apply the n to. And of course, at the moment, it's written in Cartesian form, and I don't really like that. I want it in polar form, so that's my first port of call. And in order to do that, I must draw a sketch. So here's my minus 1 minus root 3i on my argand diagram. And I know that I have to find its modulus and its argument. So the modulus is 2. And when I go to find the angle, then I have to just watch out, because when I drop my line to my real axis, I can see that the angle created is not the theta angle that I want. I'm going to call it alpha. I'm going to find alpha, and then I'm going to add it on to 180 in order to get the full rotation of the argument. And since alpha is 60, theta is 240. So now I write the complex number minus 1 minus root 3i in polar form. And when I go back to look at what I'm required to do in my question, which is to apply a power of a half to it, well, now the fact that it's in polar form makes that quite achievable. So I put the same power on the modulus, so 2 to the power of a half, and I multiply the half by the angle, but just make sure now that you write the angle in its general form. So plus n360 has to go in before that half gets written down as well. So without the two of those elements, you won't get the correct answer. So here is my complex number in polar form with those halves all applied. Again, you can see in the sign term that I've got plus n360. That's really important. So now I'll apply all those halves. So I'm going to have square root of 2 cos 120 plus n180 plus I sine 120 plus n180 as well. So at this stage then I have to just apply those n's. So again, I'm going to always start at n equals to 0, and I'm going to put in the same number of n values as there was in the original question, or as the value that was mentioned as the power in the original question. So if I look back here, I'm looking at a power of a half. That tells me I should be using 2 values for n. So my values for n are n equals 0 and n equals 1. I sub the 0 in and then just tidy slightly. So my first solution is root 2 cos 120 plus I sine 120. When I sub in 1, I'm going to get root 2 cos 120 plus 180 and I sine 120 plus 180. And again, one last little bit of tidying up to get the final solution. Like I said previously, sometimes in the question they'll instruct you to write your answer in the form a plus bi. If we look back to our original question here, we're not instructed to do that, but just note that this is like a bit of maths etiquette, if you like. The way that they gave us the question was in Cartesian form. So it's kind of good manners to give back the answer in Cartesian form. So that's what I'm going to do. That said, they didn't give me a strict instruction, so I wouldn't lose any marks if I didn't in this case. However, if they did say to do it, I would have to do it. So just for the sake of completeness, I'll do it here. And so in Cartesian form, my final answers are minus 1 over root 2 plus root 3 over root 2i, and 1 over root 2 minus root 3 over root 2i. Just to note, this is not the way that the solutions will look on your calculator. We've discussed before how root 2 over 2 is the same as 1 over root 2. It's fine to write your answer down as root 2 over 2, but it's important that you know how to convert it into 1 over root 2. So that's what I've done there with the first term, the real term, if you like, in each of those complex numbers. On your calculator, it says root 6 over 2 for root 3 over root 2. So I wonder how you'd get from root 6 over 2 to root 3 over root 2. So it would be a good exercise for you in surds to actually see, can you figure out how to make that jump? So just to review that example, things to watch out for. First of all, just make sure that you don't make the error that just because there's a squared mention in the statement that you assume that you're squaring your complex number doesn't necessarily mean that you are. In this case, as we can see, we're actually square rooting. Remember, it's not a bad plan to write down de Moivre's theorem so that you have it in front of you on the page. Of course, you have to change your complex number into its polar form in order to be able to apply de Moivre's theorem. You mustn't forget about general form when you're applying de Moivre's theorem when there are roots involved. So only when it's a fraction power. So if I was squaring or cubing or getting a power of 5, I wouldn't have to do this. It's only if I've got a fraction power that this n360 has to go in, but it does have to go in that case. Remember to use the correct number of values for n, starting at n equals to 0. And finally, if it's required by the question, just make sure to give your answer back in Cartesian or rectangular form again.